of leptons was 3 pages long, and you could paste his equation into any textbook today and it still works. So the excuse often given is that there are no Planck scale experiments available to make predictions for, but that I find a little weak, because the goal of studying quantum gravity was pushed very hard by string theorists, and I think the community is responsible for also discussing methods to detect quantum gravity effects, maybe not today, but maybe in the future, real experimental methods. So I'm done, but I'd like to show you, because I don't think many people know about these papers, that within astrophysics, optics, entanglement, cold atoms, every kind of experiment can open up this frontier of quantum gravity. And there are papers, it's not that there aren't papers, there are a few, but you see that they're very explicit in their titles about what they claim. And some of them at least have known and very respectable authors. So one is on de Sitter quantum loops, one is on quantum optics. Here is a paper on spin entanglement, a paper on tabletop experiments for quantum gravity, and a paper by actually Eric Volinde and Catherine Zurek on observable signatures in interferometers. And honestly, I think I'm as guilty as the rest of the community, not having spent any time to think about these things, but I'm putting it out there just to say that I don't think the problem of quantum gravity is over, even though string theory hasn't done as well as it might have, and experiments haven't yet done anything on this. The future is still in the future. So thank you.
Thank you very much, Professor Mukhe. I'm sure there are many questions, but because of time, we can only allow one or maybe two, very short ones. If there any detailed discussion, please catch Sunil Mukhe outside.
Outstanding talk. What you said, the error had been in formulating on Minkowski rather than on asymptotically de Sitter, which you think is now established. My question is, how do you ensure unitarity of this matrix if indeed there is no future infinity as in asymptotic de Sitter?
Yeah, I don't know. I mean, that itself is a very complicated subject. I think it's beyond me to say. Okay, whether that's an error, maybe I shouldn't have called it an error.
Turn the question around.
Yeah.
One had hoped, everybody had hoped that string theory might offer some illumination on the question of this general coordinated variance, which allows of the cosmological constant problem. But as you noted, formulations have been in simple Minkowski space, etc. Do you see any possibility of progress in a more dynamical formulation with an arbitrary background?
Yeah, I mean, there's no reason why not in principle. It's just, I think it's a matter of technical level of difficulty. So, I mean, the correct thing I should have said is to incorporate a cosmological constant into the model, or whatever the observations are which people consider to be a cosmological constant. It can be quite agnostic.
Thank you.
Very nice talk, Sunil. Very nice summary of the history, which was learned some effort earlier. But there was a couple of points which I wanted to point out in the history. First of all, when you said that superstrings provide a consistent high-energy ultraviolet picture, including gravity. Now, you remember that there was this work by Gross and Mendes, right? So it's perturbation theory you're talking about, but that has a limitation because you can't sum the perturbation series. And that means that in addition to perturbation theory, in addition to those excitations which are perturbative, there must be a huge class of non-perturbative excitations, which were the deep brains which you mentioned, but they're too related, right? So to say that high energy picture is peachy is not quite accurate.
Okay, I probably oversimplified everything in the talk, but you're right, I agree with you. But you know, a few orders of perturbation theory would be nice to do, and that's not something we can do in Einstein gravity.
Yeah, okay. The second question I had to do with black hole entropy. Now, of course, you mentioned the classic work of Strominger and Vafa, and also Schulzen and Witten and so on. But you remember that their work was done in 5 dimensions for a class of black holes which are unphysical, maybe extreme black holes. In fact, there was a lot of difficulty in reproducing the entropy, even the area law, for a non-rotating four-dimensional black hole without extreme gravity. On the other hand, there was another parallel development, which is called gravity, where not only was the area law found, but corrections were found, which were actually more accurate than the area law itself. So, is that a big deal? I mean, now that we've seen everything.
Well, corrections are known to the area law also from the string theory side, but I agree that that's limited largely to the extremal case. I'm not sure that limitation is still completely there, but probably.
Well, I had a conversation with the folks saying years ago, that's still the case.
Okay, I think the chairman is waiting for us to take this discussion offline.
Last comment.
It's not a question, it's just a simple comment. I have sat through string theory talks many, many times. And the string theory gets lost in the jungle of mathematics without any understanding what the hell is going on. I must congratulate you today on this outstanding talk because you have somehow filtered so clearly where you stand. Thanks a lot.
Thank you, and let's invite the next speaker on in the center. Before you start with your presentation, I think the organizers would like to greet you with a token.